Dear students, Assalamu alaikum. This video is the continuation of my previous lecture video on heterocyclic compounds. Today I shall discuss about a 5-member heterocyclic compound, that is pyrrole. We can see the structure of pyrrole in this slide. The pyrrole contains one heteroatom, that is nitrogen, at number 1 position. Actually, pyrrole structure is similar with cyclopentadiene. If one of the carbon, that is at number 1 position, carbon of cyclopentadiene is replaced with nitrogen, in that case it will turn into pyrrole. From the structure of pyrrole, we already saw that it is a heterocyclic compound, but pyrrole is a aromatic compound also. For a molecule to be aromatic, it must follow 4 basic criteria. That is, the compound should be cyclic, it must have a p orbital on every atom in ring, the compound must be planar, and the compound must possess 4n plus 2 pi electron according to Haeckel rule. From the figure we can see that pyrrole is a aromatic compound because it follows the 4 basic criteria for aromaticity. This compound is a cyclic compound, this compound is a planar compound, and every atom in the ring have p orbital, and it follow the Haeckel rule. That is, pyrrole contains 4n plus 2 pi electron. If n equal to 1, in that case the number of pi electron according to Haeckel rule should be 6, and we can see from the figure that the total number of pi electron on pyrrole is 6. That means the pyrrole is an aromatic compound. And we can see from the figure that the lone pair electron on nitrogen is present on p orbital. Due to the lone pair of electron present on p orbital in pyrrole, it can overlap with the p orbital on the adjacent carbon, and when it try to share its lone pair of electron to the adjacent carbon, in that case this pi bond the pi electron of the pi bond will shifted to this carbon, and this carbon will become negative and this carbon will become positive, and after that nitrogen can easily share its lone pair of electron with this carbon, and it will form a bond, and the charge of nitrogen will be positive because it share the lone pair of electron, 2 electron to the adjacent carbon. So after that, when this carbon become negative, it tries to share its excess electron to its adjacent carbon. When it tries to share its adjacent electron to the adjacent carbon, in that case the pi electron of this bond will be shifted to this carbon. That is, this carbon will become negative and this carbon will become positive, and then this negative carbon can share its excess electron to the adjacent positive carbon and can form another bond, and this negative charge will shifted from this position to from this position. So after that, this negative carbon can share its excess electron to the adjacent nitrogen. So when it tries to share its excess electron to adjacent nitrogen, and in that case, due to the influence of this, the pi bond, the pi electron on pi bond between nitrogen and this carbon will be shifted to this carbon. That is, this carbon will be negative, and then this negative carbon can share its excess electron with nitrogen and can form a double bond, that is pi bond here. So the negative charge shifted from this position to this position, and after that this negative carbon tries to share its excess electron to its adjacent carbon. So due to the influence of this excess electron sharing, the pi electron on this pi bond will be shifted to this carbon, that is this carbon will be negative and this carbon will be positive. So then and then this negative carbon can share its excess electron to this positive carbon and can form a pi bond, that is double bond. So after that we can see that this negative charge will be shifted to from this position to this position. So these are the 4 resonance contributor of Pyrrole. That is, due to the sharing of the lone pair of electron on nitrogen, the electron density of the on the Pyrrole ring will increase in this 4 carbon, that is 2, 3, 4 and 5 position. And this is another the reason, due to the increase of electron density in 2, 3, 4 and 5 position, an electrophile can easily attack on this 4 position, that is 2, 3, 4 and 5. Now about the preparation of Pyrrole. Here I showed 3 methods for the preparation of Pyrrole. In first method, we can see in this slide that when acetylene and ammonia gas pass through a red hot tube, that is at very high temperature, and the temperature is around 400 to 500 degrees centigrade. In that case, the cyclization occurs between 2 molecules of acetylene and 1 molecule of ammonia, and in that case Pyrrole will be produced. Actually, at this high temperature, the one of the pi bond between the 2 carbon of acetylene will be broken, and the shifting of this pi electron, for example, if the pi electron shifted to this carbon, in that case this carbon will be negative and this carbon will be positive, that is after shifting of the pi electron of 1 pi bond. Similarly, in that case, if the pi electron shifted to this carbon become negative and this carbon will become positive. So after that, this negative carbon can share its excess electron to this electron deficient positive carbon and can form a bond. And here the positive carbon can share the lone pair of electron which is available on nitrogen of ammonia. So due to the sharing of the lone pair of electron, this positive carbon can form a bond with this nitrogen. So in that case, there will be no positive charge on this carbon, because for the bond formation between this carbon and nitrogen share 2 electron, that is its lone pair of electron. That's why the charge of this nitrogen will be positive. So after that, this positive nitrogen seek excess electron from some other atom to regain for its lone pair of electron. So it can share the negative excess electron on this carbon, that is this negative carbon share its excess electron to this positive carbon, because their distance is very close. Due to close proximity, it can share its excess electron to this carbon. So it can form a bond with this carbon and nitrogen. So after that, cyclization occurs and Pyrrole will be formed, and by this method we can prepare Pyrrole like this. In the second method, we can see that the starting material is succinylate. So succinylate in reaction condition will be converted to 2,5-dihydroxy Pyrrole, because succinylate contain 2 carbonyl group, and due to the presence of this 2 carbonyl group, some rearrangement occurs within the succinylate, and after rearrangement, succinylate will convert it to 2,5-dihydroxy Pyrrole. For example, if we consider the 1 carbonyl group, because in both sides same type of rearrangement will be occur. So we know that the bond between the carbon and oxygen of carbonyl group, one bond is sigma bond and another is pi bond, and oxygen is highly electronegative and it contains lone pair of electron. Due to its electronegativity, it withdraw the pi bond to pi electron from the pi bond towards oxygen, and this oxygen will become negative and this carbon will become positive. So this negative carbon tries to share its excess electron to someone to become stable, and this positive carbon also tries to withdraw electron from some atom to neutralize its charge. But this carbon is bonded to this 3 position carbon, and this carbon contain 2 hydrogen, that is 2 bond between this carbon, between carbon and hydrogen, like this. For example, if we consider one bond between carbon and the hydrogen is very near to this oxygen in 3-dimensional structure. So in that case, negative oxygen tries to share its excess electron to hydrogen, but electron is not still electron deficient, and this positive carbon tries to withdraw electron from its adjacent carbon, but this carbon not yet electron rich. So due to the simultaneous effect of this negative oxygen and this positive carbon, the bond between carbon and hydrogen, that hydrogen which is close to oxygen, is broken, and it becomes, the hydrogen become positive, that is it separates proton, and this 2 bonding electron shifted to this carbon, that is this 3 position carbon become negative. So after this bond breaking, this negative carbon share its excess electron to this carbon and can form a bond, and after that there will be no charge on these 2 carbon, and this negative oxygen then and then share its excess electron to this hydrogen, that is a form bond, and it becomes hydroxyl group like this, and this portion become like this. And same thing happen in this case also. So after this rearrangement, succinylate will convert it to 2,5-dihydroxy Pyrrole. After that 2,5-dihydroxy Pyrrole will react with zinc dust. So zinc dust diffuse at this position, that is it can absorb the oxygen from this hydroxyl group and can form zinc oxide. So it this 2,5-dihydroxy Pyrrole will be converted to Pyrrole, and zinc will absorb the oxygen and will be converted to zinc oxide. In the third method, the starting material is succinic dialdehyde. Actually this reaction is similar to the step 2 reaction little bit, because succinic dialdehyde also contain carbonyl group. So due to this presence of this 2 carbonyl group at reaction condition, rearrangement occurs in succinic dialdehyde also, and after rearrangement succinic dialdehyde will convert it to diindiol, because in succinic dialdehyde the carbonyl group there is a 2 bond between carbon and oxygen of carbonyl group, and we already explained that the oxygen, due to its high electronegativity, withdraw the pi electron between carbon and oxygen, and this oxygen become negative and this carbon become positive. So this negative carbon tries to share its excess electron to an atom who is electron deficient, and this positive carbon tries to withdraw electron from other atom which is electron rich, who has extra electron on it. But the adjacent carbon of this positive carbon is this carbon. It contains 2 hydrogen, that is 2 hydrogen bonded with this carbon. If 3-dimensionally consider, one of the hydrogen is bonded like this, that is that hydrogen is very near to oxygen. in that case oxygen tries to share its excess electron to this hydrogen, but this hydrogen is not yet electron deficient, and here this positive carbon tries to withdraw electron from this adjacent carbon. If the carbon is electron rich, in that case it can withdraw the excess electron towards this positive carbon. Due to this simultaneous effect of this negative oxygen and positive carbon, the bond between this carbon and hydrogen will be broken, and this hydrogen will be separate as proton, that is positive charge, and the bonding electron will move to this carbon. This carbon will become negative, and this negative carbon then share its excess electron to this positive carbon. After that there will be no charge, and this separated proton can share and the excess electron which are present on negative oxygen, that is negative oxygen can share its excess electron to this proton and can form bond, that is this portion will be converted to hydroxyl group like this, and here two bond will be formed between these two carbon. So like this rearrangement, succinic dihaldehyde will be converted to dienediol. After that dienediol will react with ammonia. So ammonia react with this dienediol, and from dienediol and reacting with ammonia, 2 molecule of water will be released, and nitrogen will occupy this place, and this dienediol will convert it to pyrrole. During the separation of 1 molecule of water, here will be 1 molecule of water, and the ammonia will replace this position, and this oxygen and 2 hydrogen from ammonia will form another molecule of water, that is 2 molecule of water will be released during this reaction, and we will get pyrrole. So using these 3 methods we can prepare pyrrole in laboratory as well as commercially also, but for commercial preparation this method is preferable for commercial purpose. Now about the properties of pyrrole. Pyrrole is a nitrogen containing heterocyclic compound, but it behaves as weak base as well as weak acid. At pK value of 3.4, pyrrole behave as weak base, and we know that base react with acid and form a salt. When pyrrole react with hydrochloric acid, it form a salt pyrrole hydrochloride like this, and we know that hydrochloric acid after dissociation it will release a proton, and a chloride ion will also be formed. So after that this positive proton will share the lone pair of electron which are present on nitrogen, and it will form a bond with nitrogen. So after bond formation there will be no positive charge on hydrogen, but there will be positive charge on nitrogen, because nitrogen share its lone pair of electron to form bond with the proton. So after that this salt will be formed. So after this salt formation, this salt, because the nitrogen containing positive charge, this portion can act as an electrophile and can attack another pyrrole. So after attacking with another pyrrole as an electrophile, this portion can do electrophilic substitution like this, and this type of chain elongation will occur with another molecule of intact pyrrole. So after polymerization, a long resin, brown color polymer, that is resin, will be formed. So we will discuss about this property in the next slide. Now when pyrrole behave as weak acid, that is at pK value of 15, pyrrole behave as weak acid. As weak acid, it must react with a base. For example, if pyrrole react with base potassium hydroxide after dissociation will produce potassium ion and hydroxyl ion. So, and pyrrole as it behave as a acid, so acid must release proton. we see there is a bond between this nitrogen and hydrogen, and nitrogen contain lone pair of electron, and due to its high electronegativity it can withdraw the bonding electron between nitrogen and hydrogen, and after withdrawing the bonding electron between nitrogen and hydrogen, hydrogen will become positive and this nitrogen will become negative. So after proton release, this positive potassium can tie up with this negative nitrogen and can form a salt like this, which is pyrrole potassium, and this separated proton can form bond with the hydroxyl ion using the excess electron on hydroxyl ion and can form one molecule of water. So we can see here that pyrrole behave as a weak base and as well as a weak acid. As pyrrole is an aromatic compound, like other aromatic compound, pyrrole also undergoes electrophilic substitution reaction. During electrophilic substitution reaction, which position of pyrrole will be preferred by an electrophile? In the resonance contributors of pyrrole in the previous slide, we saw that electron density increase in 4 position, that is at 2, 3, 4 and 5 position of pyrrole when nitrogen share its lone pair of electron to the ring. So when an electrophile will attack, it can attack any of the 4 position, that is 2, 3, 4 or 5, but we can see from the structure that actually 2 position is symmetric with this 5 position and 3 position is symmetric with this 4 position. Actually only 2 position is available for the attack, or that means for electrophilic substitution reaction or when an electrophile will attack pyrrole, that is position 2 and 3. Now which position will be preferred by the electrophile? Let us consider what will happen at position 3 when an electrophile attack at that position. So when electrophile attack at this position 2, in that case this resonance form will be produced, and from that another 2 resonance form will be produced due to the delocalization of the pi electron. And when an electrophile attack at position 3, in that case these 2 resonance form will be produced, and we know that when a compound possesses more resonance form, at that position that compound is more stable. We see when electrophile attack at position 2, it forms 3 resonance form, and when an electrophile attack at position 3, in that case 2 resonance form will be produced. So from this resonance form we can say that the 2 substitute product will be the major product in case of electrophilic substitution reaction. That means during electrophilic substitution reaction, electrophile will attack at position 2, that is the preferred position is 2, and 2 substituted product will be the major product. The percentage of the substituted product will be the 2 substituted product will be the major product, but 3 substituted product will also be formed, but its percentage is lower than 2 substituted product. So we can conclude that during electrophilic substitution reaction, in case of pyrrole, the 2 substituted product will be the major product. During organic synthesis with pyrrole, we should avoid strong acid. We know strong acid promptly release proton. So proton act as an electrophile. So this proton will attack the carbon-carbon double bond of pyrrole, and after electrophilic substitution this type of compound will be produced. In that compound we can see that nitrogen carry positive charge. That means this compound behave as an electrophile. This electrophile can attack another intact pyrrole molecule, and after electrophilic substitution, and we already know that during electrophilic substitution reaction the preferred position is 2. In that case, 2 substituted product will be produced. That means this kind of dimer will be produced, and we can see the nitrogen of this dimer also carry positive charge. That means this dimers also behave as an electrophile, and it can attack another intact pyrrole molecule, and after electrophilic substitution reaction it will form a trimer, and in every step the electrophile attack with another intact pyrrole molecule, and chain elongation will occur, and this reaction will continue to give a polymer, that is polymerization will occur, and this polymer is one kind of resin and its color is brown. We already discussed about this property in the previous slide. Here we can see another type of reaction of pyrrole, that is halogenation reaction. When halogenation reaction occurs, halogen attack pyrrole ring as an electrophile, and 2 substitute product will be the major product according to the electrophilic substitution reaction, and we also already know that the 2 substitute product will be the major product. But there is a problem if we react pyrrole with halogen. If we use pure halogen, and we know that halogens are highly reactive due to its high reactivity, halogen can substitute every possible position on pyrrole, that is 2, 3, 4 and 5. In that case, 4 position substituted product, that is there is a chance of polyhalogenation if we cannot control the concentration of halogen. We have to strictly control the concentration of halogen. We should never use slightly excess amount of halogen also. If we use excess halogen, in that case polyhalogenation will occur. But if we want to get only 2 substituted product with halogen, in that case we have to strictly maintain the concentration of halogen. We should not use excess amount of halogen. If we use excess amount of halogen, in that case polyhalogenation will occur, it's must. And to avoid these difficulties, if we want to do halogenation and want to get 2 substituted product, in that case it's better to use the derivatives of halogen, not pure halogen. And concentration also, you have to maintain the concentration in that case also. So it's better to use derivatives of halogen to get 2 substituted product, and you have to control the concentration. Otherwise there is a chance of polyhalogenation, and in excess amount of halogen or the derivatives of halogen, in that case 2, 3, 4, 5 substituted pyrrole will be produced after halogenation. Here we can see some example of electrophilic aromatic substitution reaction. As we already discussed that in case of organic synthesis with pyrrole, we should avoid strong acid, because if we use strong acid, it will polymerize the pyrrole molecule and will form a long chain polymer, that is resin. That's why you have to avoid strong acid when you want to do some reaction with pyrrole. For example, if we want to do nitration with pyrrole, usually for nitration we use strong acid, nitric acid and sulfuric acid, combination of these 2 strong acid. As we already know that you have to avoid strong acid, but if you want to do nitration, in that case you have to use the another compound which can produce nitronium electrophile. So for nitration, as we have to avoid strong acid, we can use acetyl nitrite in acetic anhydride at 5 degrees centigrade. In that case, this nitronium electrophile will substitute the 2 position, that is 2-nitropyrrole will be the major product after electrophilic substitution reaction. Similarly, if we want to do sulfonation, as we cannot use a strong sulfuric acid for sulfonation, usually we use sulfuric acid, strong sulfuric acid for sulfonation. So as we have to avoid strong acid, so in that case, if we want to do sulfonation, in that case we can use sulfur trioxide. So sulfur trioxide, after conversion, it will convert to sulfonyl group, and as an electrophile, the sulfonyl group attack at the position 2 of pyrrole, and 2 substituted product will be produced. So if we want to do sulfonation, in that case we cannot use strong sulfuric acid, we can use sulfur trioxide for the electrophilic substitution reaction, that is for sulfonation. If we react pyrrole with benzene diazonium chloride, and we can see from the structure that there is an positive part, that is diazonium part, which charge is positive. That means it acts as an electrophile, and we know that electrophile attack at position 2 of pyrrole, and in that case this diazonium electrophile will attack the 2 position of pyrrole, and this type of 2 substituted product will be produced, one kind of azo compound. So all these are examples of electrophilic substitution reaction. Here also I showed some electrophilic substitution reaction. The first reaction I showed here is Reimer-Tiemann formylation reaction. We know that when we do Reimer-Tiemann reaction with an aromatic compound, a aldehyde group will be substituted at any position of the aromatic compound. In case of pyrrole, if we maintain the condition of Reimer-Tiemann reaction, that is if we react pyrrole with chloroform and potassium hydroxide, in that case the aldehyde group will be substituted at position 2 according to Reimer-Tiemann reaction. And all of you already studied the mechanism of Reimer-Tiemann reaction in your previous subject, so that's why I am not discussing the mechanism of this reaction. Similarly, when we do Getterman-Koch reaction with pyrrole, in that case also the same type of product will be produced like Reimer-Tiemann reaction. So during Getterman reaction, the reacting substance are different than Reimer-Tiemann reaction, that is pyrrole or any aromatic compound will react with hydrogen cyanide and hydrochloric acid, and after hydrolysis with water, an aldehyde group will be introduced to the aromatic compound, and in case of pyrrole, that aldehyde group will be substituted at position 2, as we already know that in case of pyrrole, 2 substituted product will be the major product. So in both cases, when this aldehyde group is substituted in the aromatic ring or pyrrole, because pyrrole is also an aromatic ring, this group attack as an electrophile. This is also one kind of electrophilic substitution reaction. Next reaction is the example of Pyrrole-Kauf's acylation reaction, and we know that during Pyrrole-Kauf's acylation reaction, an acyl halide will react with an aromatic compound. In case of pyrrole, when pyrrole react with acetic anhydride, in that case acetyl group as an electrophile will be produced from acetic anhydride, and that electrophile acetyl group will attack the 2 position of pyrrole, and this 2 substituted product will be the major product after Pyrrole-Kauf's acylation, that is an alkyl aryl ketone will be produced. This is also an electrophilic substitution reaction because this acetyl group attack the pyrrole ring as an electrophile at position 2. Next one is the bromination reaction of pyrrole. If we react pyrrole with bromine, in that case there is a chance of polybromination. We already mentioned about this polyhalogenation problem in the previous slide of this video. because after dissociation of bromine, bromine will produce bromonium ion and bromide ion, and this bromonium ion will attack the pyrrole as well as other aromatic compound, and electrophilic substitution will occur. Normally, to substitute product will be the major product, but we already mentioned that halogens are very highly reactive substance, and due to its high reactivity, it occupies every position of pyrrole. That is, 4 substituted product will be produced. That is, there is a big chance of polybromination. To avoid this difficulty, we can use the derivatives of bromine if you want to get 2 substituted product, that is 2-bromo-pyrrole. And another important thing is that we have to maintain the concentration. Even we use the derivatives of bromine, in that case also we have to maintain the concentration. A slight excess amount of halogen or the derivatives of halogen will produce polyhalogenated or polybromo compound. That's why we have to strictly maintain the concentration of halogen. That's all for today. If you like my lecture video, then don't forget to click the like button. You can also share this video to your friends and can also put your comments. Lastly, don't forget to subscribe my channel. Your subscription will encourage me to make more lecture video for you all. Thank you.